let us continue. So, does anybody remember, second quadrant? What were we discussing? These folks. What was the last class about? Next time we'll discuss it. I'm going to increase the entropy of the class by using you guys here and those guys here, etc. What have we been discussing? The electrostatic potential of what? Great. Okay. We were discussing about, first we did the steady and non-steady state of statements, and after that we discussed Higgs law, time dependent properties. Then we switched on to discussing the presentation of work of electrostatic potential, then gravitational. When we are talking about the electrostatic potential, there is an inherent assumption. What is the assumption? If we do not have charges, then the electrostatic potential will not come into being at all, right? And so what are we estimating when we shift from our standard Fick's law down to the Nernst formulation, where we are talking of an electrostatic potential? What are we essentially trying to do? We are trying to offset the diffusion. We are trying to maintain a concentration gradient across a very specific context. This is gradient. Though you can design batteries and whatnot with the same idea. Okay? Alright. So we will continue, we'll come back to that, but before that we will actually step back a little bit further. Okay? So this is an equation that you have seen. Okay? And I hope you will recognize this equation, the individual terms. We had, I think 3 or 4 classes back, we had looked at the Einstein's diffusion equation, and from there we had derived this equation, okay? And please, if you have forgotten, please recognize each term. There were 2 equations preceding that. One was mean square displacement, and the other was we had something known as the viscous friction coefficient times diffusion coefficient on the right hand side, thermal energy, okay? And when we talk of Stokes-Einstein relationship, that viscous friction coefficient is substituted by 6 pi eta A, where A is the radius of what we assume is a spherical particle. Normally all our particles are not spherical, some can be oblong, so on and so forth. But we assume it is spherical, and this works quite well. There are certain exceptions, and we are not going to travel into those exceptional regions for now. Okay? This is related to, I'll just mention it because when you read literature and all, if you suddenly hit upon this, I don't want you to be surprised. I want to at least physically correlate. Okay? This is related to something known as the fluctuation dissipation theorem. There are many formulations. We are not going into that. It's just a simple definition that I have put in here. When you are at equilibrium, okay, a process that dissipates heat, something which is more viscous will dissipate a lot of heat, okay, is directly related to another process, diffusion, associated with thermal fluctuations. So, the more the thermal energy, the faster you will diffuse, okay. But your viscosity, a dissipative process and a fluctuation process, they are related. I'm really oversimplifying this. There are many, physics articles based on this, but, you just need to kind of understand the very, basic physical picture of this. Now, there's something important that I want you to realize. So we have done those free energy calculations, remember? Free energy of a protein, active state, inactive state. And what is the typical unit of free energy of, say, a protein or a DNA or anything? Kilojoule per mole or kilocalories per mole, okay, molar units. But here, unlike, this is a question which I guess some of you will relate to. This one does not have a molar analogy. Okay, the Stokes-Einstein does not have a molar analogy, and you can see this. Oops, I hope this works. Please work. Oops. Okay, unlike, say you had delta G, proportional to, or whatever, sorry, you had things like, rate proportional to e to the power minus del G by kt, or K proportional to e to the power minus del G by RT, depending on the units. Unlike this, you do not know molar analogy. This comes from the fluctuation dissipation theory. So what you will have to do is, if and when you are dealing with this, if you have RT given, okay, you will have to divide by the Avogadro number. Okay, so this is one little place, there is an exception here. Alright, so this is something that you will have to be careful about. We'll do a few more problems as we go forward. Now, so what is the question, what is the unit that I think many of you are not yet familiar with? Diffusion coefficient, you know the dimensions, right? Length square per unit time. So if I ask you the SI unit of diffusion coefficient, you will immediately tell me meter square per second. Okay? Temperature is known, kBT is known, you know kBT is energy. So you know this is the radius. So what is the quantity staring at you which you don't know about? Or at least the viscosity units, right? So obviously when we deal with this, we have to look at this viscosity, which is a bulk measurable property. I don't know if you have done those experiments where you kind of drop something, drop a heavy ball through a column and measure the viscosity, that kind of thing, right? Alright, so what is the unit of viscosity? Can you work it out? Even if I don't help you. L minus 1, T minus 1. Okay? Why? Because viscosity is actually, any way you look at it, it's pressure into time. Okay? I will skip this, work it out, it will come down to L minus 1, T minus 1. Okay? So SI units are Pascal seconds, because Pascal is the unit of, SI unit of pressure, and seconds. So these are SI units. So this is equal to 1 kg per meter per second. But the most commonly used unit is poise. Alright? Where, or rather, or centipoise. This is known as CP. Okay? 1 poise, okay, sometimes it may also be given in centipoise, is 1 gram per centimeter per second. So this is an CGS units, right? This is the same as, please work it out, 0.1 Pascal second. This, make a note of this in your notebook. We'll use this in the next problem. Okay, please do the interconversions. You need to do that. Okay, so now if I give you, we'll present two situations. So when you have, please quieten down on that side, please. Okay. So when you have things diffusing, let's say I have very distilled water at a particular temperature, okay, and the water molecules are diffusing. What is the medium in which it is diffusing? It is diffusing in its own medium. water in water, right? Versus I can have a mixture. Okay, I can have something where I have, in addition to water, I add the little bit of glycerol. Okay, imagine the cytoplasm. Does the cytoplasm have a fixed viscosity? Do you think the viscosity of the cytoplasm is a measurable quantity? It is. But is the cytoplasm a pure entity? It is not. Right? So when you have one molecular species diffusing in a mixture medium, you have a slightly different scenario. Okay, you will have a net viscosity, but at the same time, not every particle will have the same diffusivity. Okay, because the size of the particle is coming in, that A over there. Okay, so let's say I'm doing a very simple thing, and you see that your ethanol molecule is not really a sphere, right? But we are assuming, this is an assumption that it has a radius of 4.4 angstroms. You can fit anything to a sphere and find the distance from the center. We'll approximate this as a sphere. So I'm talking of self-diffusion. So please note down this term. I'm talking of, here I have limitations. Oops. I'm talking of self-diffusion. Sorry, I can't underline that. Well, I can. I'm talking of self-diffusion. Okay. So let's say I'm talking of ethanol, and somebody has measured the ETA, the viscosity of pure ethanol at 25 degrees centigrade. How will you approximately estimate the time to diffuse across a length of 5 centimeters? And pure ethanol, 5 centimeters is, 1/3 of your short ruler. What time should I expect one ethanol molecule on the average to go from one point to the other? How will you tackle this problem? It seems very simple and it might even seem boring, but what am I going to do? I have this information, okay? This is available, okay? This is available. Find out what is the first step? Find out D. It's going to be kVt by 6 by 50. Can you please try? Yes, I have provided that as well. Correct? So you first use this equation to get to your diffusion coefficient, and then you go back to that original diffusion equation. So what only remains is to find the time. Instead of r square in this place, this is the mean square displacement, but I want my things to diffuse. Okay, so I'm going to use distance square in this case. So let's first work on the diffusion coefficient and let me know what you're getting, at least in SI units. So this is a practice I would like you guys to get. Okay? So we have to use, what am I going to put on the top? What is my Boltzmann's constant in SI units? What should I put? 2 centimeters. Now the centipoise I need to convert into SI units. Let me know if I'm doing things right.
One poise is 100 centipoise, right?
One poise is, so this should be, did I make a mistake? So one poise is 0.1 Pascal second. Right, so this should be 10, right?
10 to the power minus 2, I think.
Should it be 10 to the power minus 2?
Minus 3, I think.
No, that is centi.
So we are doing a centipoise.
One poise is 0.1 Pascal second. So
Right,
one
so-
centipoise will be 10.
Oh, okay, yeah. So this one should be
Minus 3.
Okay. So you can correct for that, but ultimately what is the value that you get for the diffusion coefficient in SI? Please get into the practice of doing these numbers quickly. And if you're not familiar with your calculator, we have a few people who say, I just got the calculator, I don't know, which button works how. That will not work. So please make sure you can do this. So you'll get some diffusion coefficient, and I believe it should be of the order of 10 to the power 5 to 10 to the power 6 meters square per second. No, sorry. 10 to the power, I gave a wrong number. How much are you getting? So you have these extreme numbers here, right? So, if I go back, this is going to be 10 to the power minus 10 something.
4.62.
Is that right? So, and the units are going to be? Okay. Now, if I do that, if my r squared, now I'm going to use this equation. Okay. Putting it here, r squared average, I'm talking of 25 into 10 to the power minus 4 meters squared. Okay. Will be 6 into this value into my time taken. So what kind of time are we talking about?
Ma'am, is this diffusion 1D or 3D?
Right. So the question is asking is it 1D or 3D diffusion? So when I'm talking of bulk diffusion, given that the molecule is extremely small, it's not even a nanometer, we have to take 3D diffusion. Unless I'm talking of an extremely nanoscopic channel, okay, where my size is comparable to the distance that it has to travel. Even if my small molecule is traversing from one end of an E. coli bacterium to another, it's still 3D. Compare the size scales, right? In a bacterium, I'm talking of microns. Here I'm talking of angstroms, right? So that is roughly 4 orders of magnitude longer in length. So here the spatial diffusion has to be 3. So my time comes down to how much? Of the order of 10 to the 0.9 into 10 to the power 6 is roughly what I seem to be getting. So that is of the order, that's a long time, right? If I divide by 3600, I'm getting what? How many hours? That's, that's quite long, right? So on the average, this little molecule will take enough time to go from one part to the other. Now, based on the same knowledge, let's look at a more specific case. This is an oversimplification, but imagine somebody did a viscosity measurement of the cytoplasm. And there is data out there where you have a mixture. Okay, here I have taken simply ethanol in a binary solvent, just water ethanol. Okay, ethanol is an organic molecule. Your cytoplasm is a mixture of many organic molecules. Okay, some biomolecules as well, right? So you see there are two patterns for the viscosity in SI units. This is either in order of 10 to the power minus 4 Pascal seconds, okay, and this is the mole fraction of ethanol to water, okay. So you see you have two different, they tend to go up and come down. You can expect your cytoplasm also to do that way. I'm not pulling up those data, but generally speaking, when you have a mixture, you have this kind of behavior. And conversely, when you have a single pure solvent, it kind of tends to go down. We are not going to get into the reasons of why that happens, but this is a very general phenomenon. And another thing, those of you who are a little bit acute in your observations, you'll find that if I raise the temperature, sorry, this would be 298. This is a typo. This is 298. This is room temperature. At room temperature, temperature, the behavior is a little bit flatter. If I decrease the temperature, it tends to go, the inflection is a bit sharper. Yes?
Cytoplasm, the blue one.
This is not cytoplasm. This is a binary mixture of ethanol with water. Please look at this. I'm telling you that if you have ternary, quaternary, if you have a mixture of many things together, you will not get a simple behavior. You will get a more complex behavior as you change the different ratios. That's all I'm trying to say. Okay, and I don't need you to understand why it is. It's a complex mechanism. But at the end of the day, for a particular mixture, for a particular composition, I'm going to get an eta. I'm going to get a viscosity. Okay? So if there are situations in which the cytoplasmic viscosity is measured, okay, or reported, okay, as a function of temperature. Yes.
Cytoplasm has like diffusion,
Yeah.
but there might be some other things which are affecting the diffusion.
Yeah, everything is affected also. There are interparticle interactions.
We cannot take the assumption that it definitely happens.
We are not assuming anything. These are measurable quantities. Somebody has measured this. If you read this part, okay, viscosity of a mixture. I'm only telling you that when you have a complex mixture, such as this is a very simple mixture, only ethanol water. You can assume a complex mixture such as cytoplasm, such as your egg white, okay, which has many proteins, ions, organic molecules, so on and so forth, okay, powders, some molecules, powders. You'll have this kind of a behavior. It goes up when you change a certain ratio. Let's say I keep everything else fixed. I increase, some kind of tehalose or something. Okay? You will have, you can expect this kind of behavior. It goes up and goes up. Clear? Yes, there was one more question over here. Yeah. Yeah, everything is included. This is just a measurement.
From that, using that analogy, if we use a mixture, then the interaction between different quantities
will change. Will be lesser, greater, I don't know. I can't entirely say whether it will be stronger or weaker.
So that's why in pure ethanol, the time is
I see what you're saying. That, if the viscosity, why does the viscosity go down? Why does it become less viscous? It's possible. That's a good rationale. I see where your intuition is working. It's possibly true. I would set that as a hypothesis rather than accepting that as a truth. No, so this is where, as you step more into research, you'll realize. You set a hypothesis, then you test your hypothesis. You can't say that just because my mind tells me this is the reason, I believe in it. You have to accurately prove it. And at the top of my mind, I have yet to read papers which give a mechanistic explanation. That is something you can follow up, in your summer project or something. Why does the viscosity go up and come down if I just change the... There are papers out there, but I can understand what you are thinking. It's probably true, but will need to be verified. Yeah.
On the two graphs, isn't the viscosity is a different temperature?
No. So these are, one moment. This is the effective viscosity of the mixture. Okay? You can measure the viscosity by doing a set of experiments. You can just take a steel ball, drop it, all those dirty experiments. I don't know if some of you have done it. And you are 10+2 along. You can measure the viscosity. So some kind of a very accurate measurement was done where the molar fraction of ethanol to water was changed. And well, those of you who lean a little bit into computations, such things can also be done in the computer. So those open circles, full symbols are computer simulation results and empty symbols are actual experimental results. They look very close or adequately close, at least the trends are similar. But the trends are different for the two temperatures. That's all I'm trying to say. Now let's say the question given to you is, what is here, one must consider, let me call it effective viscosity. Your medium could be your cytoplasm as well, right? It could be, any biological medium. It could be, you probably have some kind of a artificial agarose gel kind of business where you're trying to, feed nutrients to your bacterial cell culture. Could be a scenario of that kind as well, right? So it will depend on the medium, but just imagine a scenario where you're trying to grow a bacterial colony. Okay, you are giving some kind of nutrients, a variety of nutrients which are individual molecules. Maybe they are complex carbohydrates which can be, ingested by recognized and used by your bacterium. The different molecules will diffuse differently in the same viscous medium. That is the point I am trying to make. Okay, so if you have, let's say I fix myself here. A 0.2 medium. Okay, so let's say here, I pick up my, I have these values. Let's say I consider this value and this value. So I get my viscosities. Okay, I want to find the diffusion coefficient of ethanol and of water. So my eta will be the same, but my D could be different. D will depend on the size of the molecule. Got it? So, if you understood that, okay, I just wanted to tell you that when you have, uniform medium, this is what at typical room temperature, these are roughly speaking the diffusion coefficients. So, what do you notice? Water, if I have a hydrogen ion, it's nearly 10 to the power minus 4, and the units are not SI units, centimeters square per second. Look at the scales. When I go from H plus to say carbon dioxide, okay, I'm roughly not even reducing by an order of magnitude, right? It's 9.3 into 10 to the power minus 5, and my carbon dioxide is 2 into 10 to the power minus 5, right? It goes down by about a fifth. But if I look at more complex things, if I look at sucrose, if I look at hemoglobin, if I look at DNA, see, you have lower and lower diffusion coefficients. And this is to be expected. So one interesting experiment that one may think of doing is, what if I, plot D versus, the size. How is that going to vary? There might be data. It should be inverse, but am I talking about a linear relationship? Is it kind of going down? Those are considerations that might be useful. Okay. So if I were to ask you to consider, some of the molecules that, yes. I asked you.
Go back to the previous. I did not get the last three.
Last
They
three.
have very high mass, but their diffusion is low.
So if they are bulky, if I'm 250 kgs, then you can expect me to move much more slowly. Right? But got it? It's R square, it's length square per unit time. Okay? So consider a situation here. In fact, I have picked these pictures up from not very old paper. This is, I just took this as a representative snapshot from a computer simulation paper. So these are lipid bilayers. And we know that lipid bilayers are not perfectly permeable. In fact, you have a natural potential difference which keeps concentrations across the object. A typical lipid bilayer is 5 nanometers plus or minus a few. Okay, more than 4 nanometers, about 5 nanometers. See, 52 plus minus 2 angstroms. And these are typical. This is POPC, okay, POPC, when I have, some other stuff added in, cholesterol, this is a small peptide that they put, so on and so forth. And they have shown that, the lipid bilayer varies, okay. Now if I go back and think that I'm going to transport either hydrogen or sodium, potassium, calcium ions from one end to the other, what is the time that an average molecule will take? Okay, so if I take this as 52 angstroms and I take an Na plus here and I expect the Na plus to kind of diffuse from one end to the other. What is the time? Same principle, so you can use it. Now the question again is, should I use small d as 1 or 2 or 3? How many of you feel that d should be 1?
What?
D is the spatial,
Approximately the radius of a molecule.
These are, when I'm talking of a hydrogen ion, H plus, this is really, really tiny. Even your Ca2 plus, we are talking of a couple of angstroms. Maybe 3 angstroms. I don't exactly remember the radius of a calcium ion. Okay, maybe in your chemistry class you read that. No, they are typically angstroms. Remember that a chemical bond, this is not a chemistry class. A typical chemical bond is a few angstroms, 2 to 3 angstroms, right? What is the length of a peptide bond? Of the order of angstroms. Okay. So when you're talking about the radius of an ion, okay, it's less than an angstrom or of the order of an angstrom, right? So this is at least an order of magnitude more. But you might argue that it is, is it kind of flowing? Should I use small d equal to 1 spatial dimension? That is actually not really justified. You will have to assume that, this is entirely permeable. If my membrane is completely permeable, I have to allow small d equal to 3. Using d equal to 3, how long does it take these ions cross the bilayer? Yeah.
And if the molecules have to diffuse, don't they do it through a channel? So,
No, but here these are model membranes. We are coming to the channel part. I'm assuming that my bilayer is completely permeable, which it is not. You and I would not exist if our cell bilayers were completely permeable. That's a different story. But in any science, especially in biophysics, we make simplistic systems to understand complexity. Okay, so this is just an exercise. Alright, what about this question? Consider size to be directly proportional to the molecular weight of fluid. Okay, which I will say then that my A is directly proportional, or A cube I can say is directly proportional to molecular weight. Volume is proportional. I can do that, right? Is that satisfactory? You can. So if I say A cube, well, we can say A cube is directly proportional to molecular weight. Okay. Now I am telling you, I have given you 2 proteins, myoglobin whose weight is 17 kilodalton and hemoglobin which is 64.5 kilodaltons. Okay, what is the approximate ratio of the times taken to cover a distance of 1 micrometer in media of similar viscosities? I am not changing. Okay, assume eta is the same. If temperature of 1 and temperature of 2 are 300 and 320 Kelvin. Right? So if I have A1 cube by A2 cube equal to molecular weight of 1 by molecular weight of 2, this is, let's say, 17 by 64.5. So A1 by A2 would be 1, cube root of that, right? Is that okay? Yes.
What is exactly the size?
Huh? Size means, how massive it is. So assuming that I'm kind of making a, what is the underlying assumption I'm doing here? If you're thinking right. You can take A and, yeah, I see your point, that should I take it proportional to A or should I take it proportional to A2? Look, when am I taking A2? I'm assuming that the volume, okay, A2 is proportional to the volume, whether you consider diameter or radius, right? So if my two proteins are of the same density, protein density is the rest of the these are not rigid bodies, but still I can assume the density. In this case, so we are faced with a situation like this, I'll tell you. But for a small molecule, like radius, here I'm taking radius. No. So I've said that the volume is proportional to the mass. Assuming that the density is the same. Exactly, right? Did everybody get that? Assuming that the internal protein density is the same. I see a lot of people confused. See, I have one protein which is medium size and another protein which is much bigger. Okay. Assuming that they are roughly similarly dense. So, एक का volume बढ़ेगा तो mass भी उतना ही बढ़ेगा, right? So, and what is volume proportional to? Radius cube, na? Diameter cube, radius cube, whatever you like, right? So, if I do that, I simply get A1 by A2. If I get A1 by A2, if I go back to my known equations, you already have your 6 pi eta AD equal to kBt, right? So I have said that eta is the same. So eta does not change. So from here I have A1 D1 by A2 D2 equal to T1 by T2. Is there any disagreement over there? Can I find my A1 by A2 here? Can somebody quickly tell me what do you know how to find the cube root with your scientific calculator? How much is it? 0.641. 0.641? Good. So what I can do is 0.641. So instead of T1, I'm going to put 300. Happy? With the assumptions that we have made, we have been making two assumptions. One is that the density is the same, and these are roughly some kind of a spherical thing. So my volume is proportional to the mass is proportional to the volume. So D1 equal to how many times D2? You can fill that up. Okay? Relatively straightforward question. As far as if you understand this, even with basic math, you should be able to do it, as long as you know how to run your calculator. Now, if you don't know how to operate your calculator, you guys are looking at electronics all the time. So I expect you to be able to, use your calculator effectively. Alright, so you can do that now. Now, we have some time, so we had looked at this problem. I'm not going to do the derivation again. Where did this equation come in from? So I asked one of you in the beginning of the class. So we had started with the diffusion equation, with the Fick's law, and we had come to a point where we set the flux as 0. Okay? And we had assumed that each particle has a charge. So what is the effective potential difference which will stop the diffusion? So that I maintain a concentration difference across. If there's nothing across, Your potential difference is not maintained, things will mix. And we don't in biology, we want to compartmentalize things. You are not homogeneous. I don't know how many of you have thought about it. What are we made of? Carbon, nitrogen, oxygen, hydrogen, phosphorus, chlorine, okay, sulfur, a little bit, some ions, so on and so forth. If I take you and I blend all of you, nobody hopefully will do this in our country, but if we are blended, we are just an organic hodgepodge, right? We are what we are because we are compartmentalized. Our cells are very specific compartments. Every little cell is doing what it needs to do, right? So how's that working out? So in this case, so we have worked this out. And what is del log of C? I put this. So let's say I have a concentration here and a concentration here. Okay, so I have labeled it as extracellular compartment and a cytoplasm. There's a potassium. So usually the potassium concentration inside the cell, at least a mammalian cell, is higher than the concentration outside. For sodium, it is the opposite. Okay. So if there was no potential difference, the diffusion gradient would homogenize the potassium concentration or any ion for that matter. In this case, you have to have something which is offsetting it. So the other way to write this is logarithm of C1 by C2. Oops, sorry. I'll clean it up before I give it to you. It is the same as this formula, right? Should it be C2 by C1? C2, should it be, because you have a higher potential, well, the potential difference is in this direction, right? See, C1 by C2 is less than 1, right? Okay. So how will this plot appear? Can you tell me, so look at this plot. I have plotted log of C1 by C2 as a function of 1 by t. Can you tell me what this plot will look like? Straight line, yes. What kind of slope? Negative slope or positive slope? Negative slope, right? So it will have, I will expect it to have this kind of a following. Right? And if I change it to some other ion, what will it be? So you can think about it. Okay. So this in principle can be worked out systematically for all ions. And so when you have a cell where you have again, a large number of ions, okay, starting with the hydrogen ion, potassium, calcium, phosphate, chloride, okay, certain nitrates, okay, all kinds of charges, all kinds of concentrations, and some of them are magnesium, bicarbonate, so on and so forth. So when you have this at 310 Kelvin, and I would like you to actually sit down and just verify a few. When you do this, you will get the equilibrium potential as such. When there are certain laboratories which do electrophysiological experiments, so they actually measure these potential differences across. They have extremely sensitive instruments, and you can measure. So you have to do control experiments. You have to design certain systems where there's only one kind of ion. Okay, let's say I did a project where I make a lot of artificial cells, okay, which has only one kind of ion across. Okay, and I maintain the ion concentration as close as possible to my actual mammalian cell ion concentration. I repeat that experiment for every ion. And I look at how much voltage I need to maintain that concentration gradient. If I sum up those voltages, okay, and if it's actually the physiological concentration that you have maintained, that delta V should come down to what you have in your cell. Okay, so one exercise I would like you to do is, given this, take any of these, let's say we do C1, C2. This is an exercise we should be able to do with the Nernst potential, right? And if I have that for mixtures of ions, I can say, oops, delta V effective will be equal to, I'm going to write it like this, where I equal to 1 to number of ion types. How many ion types do I have? I'll just sum it up. Is this clear? Right? If you play with batteries, you know when you are trying to make, when you fix batteries, when you fix the polarities, one way or the other, it's going to be a mathematical sum. So you can work that out. Okay. So in the tutorial, we'll do a few more case studies, but I'm going to come back to one more problem that we talked about last class. Okay. In general, if I want to maintain a concentration gradient, I have to apply some kind of a force. And the logarithm of the concentration gradient will be force times length by kT. Do you realize that the right side is dimensionless? Right? Force into length is work, kBT is energy, so the right side is dimensionless. No, not a problem. So here by analogy, and there's some good explanation given in Nelson, how this comes about. I'm skipping the very rigorous derivation here. But when I apply a centrifuge, and I'm assuming when I do my centrifuge, I'm assuming that gravity is too weak. Okay, so my concentration gradient will not be affected if I keep it like this versus if I keep it like this. People tend to, centrifuges are designed such that, once the centrifugation is done, the supernatant so-called does not fall back immediately. There's a certain technique that is admission here. I've never done any centrifugation in my life. So, okay, you may have. I'm not an experimentalist. But at the end of the day, the G, the rotations per minute that you're applying, that is supposed to exceed anything that gravity does. Gravity is a very weak force. You realize that, okay? So when I come down to this problem, which you have already done in the last class, right? I told you, consider a solution of proteins that are of mass 50 kilodalton. Roughly 1 dalton is slightly different, but you can take it as 1 gram per mole. 1 dalton is 1 gram per mole. So when I talk of a 50 kilodalton, and very roughly speaking, 1 kilodalton of protein is roughly speaking 10 amino acids. That's a thumb rule. Anywhere between 8 and 11 something. So when I am talking of a 50 kilodalton protein, I am talking of a protein roughly 500 amino acids. It's a medium-sized protein, medium to large. Anyway, don't worry about how many amino acids. But consider a solution of proteins of mass 50 kilodalton. The solution is spun in a low-power centrifuge that achieves highest rotation of 100 rotations per minute. Okay, so we had done, and I think most of you got that there would be no difference in the protein concentration 5 centimeters away and at the axis, right? How many of you remember that term? Okay, roughly 1/50th of the class remembers that. But please revise it. Okay, it's not a hard problem to do. It is, you might want to note down that formula. Make sure your units are the same. We will practice these problems again. But please make sure this is done. Now, if I reverse it, if I tell you that my experiment demands that I have 1000 times more concentration 5 centimeters away than at the axis. Okay, which means my C of R by C of 0 is 1000, let's say. Okay, I reverse the problem. You should be able to do this as well with a little bit of transitions between here and there. So what is the RPM required for a concentration ratio of 1000? You can work it out, and I actually got, we do have a few minutes, I got maybe I made a mistake, I got 204 rotations per minute. That is roughly twice of this. Can we, in the next 5 or so minutes that we have, I will go back to the formula so that you remember it. Okay? So log of C of R by C0. C of R is the concentration at radius R from the axis. Okay? C of 0 is the concentration at the center. So if this is the axis on which over which my centrifuge is rotating, this is R equal to 0 and this is the action distance. Okay? You see, so you can imagine that this is the centrifuge axis and this is where you expect your concentration to vary, right? So it's going to vary with length. Okay? Oh, okay, sure. So M was 50 kilodaltons. Now one trick here. When I say 50 kilodaltons, what is 1 kilodalton? It is 1 gram per mole. 50 kilodaltons is 50 kg per mole. Please, everybody, people are bound to make a mistake. 1 dalton is 1 gram per mole. Okay, so I can say oxygen is 18 daltons. Oxygen below is 18 daltons. When I say my protein or my large DNA or my protein DNA complex is in kilodaltons per mole, when I talk of this particular protein, it is 50 kilodaltons per mole. So 1 mole will weigh how many? How much? 50 kg, right? Remember that your protein molecules are gigantic compared to the normal molecules that you encounter in your chemistry. Okay? And it's like that it's kgs because we have to operate with SI units. SI units might slow you down a little bit,
300.
but if you do it correctly, if you do everything in SI, you will actually make mistakes. Yes. Yes. What is a mole? What is a mole? Huh? This particular protein, I see what you're saying. Do I have an avogadro number of, say, hemoglobin? I don't have a great answer for it. Let me think about it. But I see your point. That gives me some food for thought. And I'll get back to you about it. Okay. But if you operate with this formula, what is the RPM that you're getting? It's a good point. What is the RPM that you folks are getting? 3547 rotations per minute. Okay. Huh? 3000 plus rotations per minute. Okay, so between 3 to 3,500 rotations per minute. I got 3 of those answers. If you get it ballpark in the right regime, I will be happy enough. How much does this section get? A few thousand rotations per minute. What are you guys getting? Nobody got a calculator today? Get a calculator, please. Alright, so I'm getting 3 answers which are roughly 3,500 rotations per minute. Anybody else supports that or dissents that answer? Alright, so maybe we can go over it. So I'm going to say, is that right? I'm going to put a question mark on it. We don't have much time, But I'll just quickly take 1 minute to tell you, centrifugation is a very important concept in biology. Many a times you are going to subject your entire cells to centrifugation because you want to separate all the components. So generally, I don't know if some of you have heard of the sweat bug. Okay, people with microbiology background and all, they would have heard of. Please quieten down. I'll just take 2 minutes. You may have heard of sweat bug units. In fact, the person after whom it is named got a Nobel Prize in Physiology Medicine. A Swedish gentleman called Svedberg. The idea is, if I have some kind of a vessel of this kind, what is the force acting this way? Gravitational force, right? Mg rather. And there's going to be an upthrust. Okay, there's something against flotation. So M net is M minus rho times Vg, where rho is the density, which is this rho here, and V is the drift velocity. We will not go into much detail. So assuming that we are talking of water, okay? Now, and what is this zeta? How many of you remember this? How many of you recognize this guy? Viscous friction coefficient. Okay? That is Einstein's relationship. We simply had this guy times capital V equal to V. This is that same guy, viscous friction coefficient. Okay? I don't know who's coming, but this is. So all said and done, do you agree that this will have a dimension of time? So Svedberg, so this is very counterintuitive. I'm talking about the sizes of biological particles. Okay? But I'm using a time unit to characterize those particles. And if you look at, I'll show you one more slide. See, there are you all know about the inner structure of the cell. If you look at it, by the way, it's known as sedimentation coefficient, sweat. S stands for Svedberg, but it is actually a sedimentation coefficient. You see, these are the sedimentation coefficients of all of you. Okay, I will leave you with a question. So the larger an entity, should it have a greater sedimentation coefficient or a lesser sedimentation coefficient? We'll get back to that tomorrow. Okay. Another question for those who are paying attention, the larger your particle, let's say an organelle versus a small protein, which will have a greater S, which will have a greater Svedberg number. That is the first question. The second more profound question is, when you have a biological, when you have something which is composed of two other things, okay, think of the ribosome. You have a small subunit, you have a large subunit. If you were to find the Svedberg number of the small subunit separately and of the large subunit separately, that total will not be the effective Svedberg of the large subunit. Why? Okay? Think about that and we'll come back to it tonight. Okay? Alright, so we will end here.